Saturn is the great ring planet. Until the Voyager missions, we did not know simple facts, such as the approximate number of rings circling the huge planet. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio, and I'm your host for this program, Voyager 2 Saturn Encounter, which is the 12th in our 13-part series, Journey Through the Solar System. Saturn is the 6th planet from the Sun and is the 2nd largest planet in the solar system. As we saw in our previous program, the Pioneer spacecraft gave us our first good views of Saturn, but the pictures did not have enough resolution to show the planet's rings and moons as clearly as the later Voyager pictures did. In late 1980, the Voyager 1 spacecraft made its close encounter with Saturn. About 10 months later, the Voyager 2 spacecraft also flew by the Great Ring planet. Voyager 2 produced thousands of pictures of Saturn and its rings and moons from different angles and distances than did the first Voyager spacecraft. Now let's see the saga of Voyager 2 as the story unfolded in late August 1981.
The spacecraft has journeyed 1 billion miles from Earth in 4 years. The beauty and complexity of the ringed planet and its family of satellites was first revealed by Voyager 1 in its November 1980 encounter. Now, Voyager 2 will closely explore specific targets in Saturn's realm. We join Voyager 2 on its approach as the spacecraft cameras and other instruments scan the planet and most of its 17 known moons.
Good morning. At 8 o'clock this morning, Voyager will be 1,700,000 miles, that's 2,700,000 kilometers from the cloud tops of Saturn, and it's closing in on the planet at 26,500 miles per hour, which works out to 11.9 kilometers a second. And that makes it still just under 1 billion miles from Earth, 965 million miles away.
The young lady right there.
Questions. First for Dr. Smith. On the screen yesterday afternoon on the limb of Saturn, I saw a lot of white flecks on the image of Saturn. Do you have any idea what those were?
Well, there are, particularly at the higher latitudes, a large number of these small white features, similar to many that we saw on Jupiter. They may be small convective elements, like a large aggregation of thunderheads or cumulus-type clouds. The resolution was probably something in the order of 100 kilometers or so that gives you an idea of the scale of those features. It's similar to what we've seen in Jupiter's atmosphere as well.
Good afternoon. At 2:30, the Voyager is a little over 900,000 miles away from the Saturn atmospheric surface, and going about 28,500 miles an hour toward Saturn. All is working well. We have been watching recently, and will continue to see for a little while longer, some photopolarimetry of Saturn. Actually, what we're seeing are the backup photographs that go along with the photopolarimetry scans. These are going north to south across the surface of the planet, and we're looking for the information we get from the photopolarimeter instrument, quite a bit of which has to do with the nature of the particles, the size and characteristics of the particles that make up the high haze layers and the upper portions of the clouds.
Saturn's rings are targeted for special study throughout Voyager 2's approach. Sections of the braided F ring are studied from different points of view to create three-dimensional pictures of the strands of the ring. Dark, spoke-like features in the B ring are photographed as they move around the planet.
There we go, coming around the racetrack. Now, briefly in front of the planet, then coming around again. Okay, now there are at least a few places where we think we see, this is going a bit too quickly, but where we think we see, right in here, instantaneously, almost instantaneously, the production of a radial spoke. There's another one right there. Wasn't there before, suddenly appears, right there, momentarily radial.
If you see them, it will be startling.
The spoke-like features of the B ring, discovered by Voyager 1, are an important focus of study during this encounter. These members of the Voyager imaging team want to glean all they can from Voyager 2's photographs during 14 hours of the spoke's movement around Saturn. Another phenomena they want to look for are possible additional satellites that might be embedded in the rings. 2 deep gaps in the Cassini division and one in the outer part of the C ring might be just the spots for such satellites.
That same set of pictures, incidentally, is the one that we use to look for embedded satellites in the gaps, in these clear regions, in the Cassini division in the outer edge of ring C. And the ones that Len Tyler pointed out are, in fact, the very ones that we're looking into. The ones he sees as free space, we also judge to be almost completely free of material. And it's within those regions that we're looking for these embedded satellites, which we would calculate ought to be in the vicinity of 30 kilometers in diameter. Well, a progress report on that is that Terrell has now completed 1/3 of both rings in the Cassini division and the outer edge of ring C, very, very carefully, where he believes he can see anything down to 5 kilometers, certainly, and possibly a little bit smaller, and that assumes that the particle is even a little on the dark side of average for the rings, and nothing in that 1/3. Cuzzy, within the Cassini division only, has looked at the remaining 2/3 of the Cassini division, not quite as carefully. His limit is probably something of the order of 10 kilometers, but still quite a bit smaller than, the limit is quite a bit smaller than what we were looking for, a 30-kilometer satellite. Because he did not find any satellite larger than 10 kilometers in either of the gaps in the Cassini division, and we now find ourselves at a point where we had hoped not to be. Included in this image of Saturn are actually 4 satellites. 3 of them show up quite readily: Tethys, Dione, and Rhea. And this is the shadow of Tethys up here. But if you look very carefully, you'll see a little bright spot right here. That's Mimas, and its shadow is seen up here. This is reduced in false color because it gives us a little more contrast to the features that we're looking at. The colors that go into this are ultraviolet, violet, and green, and again indicate the way Saturn might appear if our eyes were sensitive to the shorter wavelength part of the spectrum. Once again, we see this high-velocity jet, this looping feature indicative of that high-velocity jet blowing toward the east about 150 meters per second. Down below is a much weaker jet toward the west at about 15 meters per second, and then these anticyclonic features that are caught up in the shear in between. This brownish spot moving along at about something like 30 meters per second in a easterly toward the east. Note that when we look at these objects into the UV, that this brownish spot tends to have a slightly brightest center, and these 2 features show up quite well, and that's in contrast to the green image, black and white green image, that I'll show you in just a moment. Note the position of these 2 features. This is about the same latitude as this one, and so they're moving along more rapidly than this feature, which is almost standing still in between this strong jet that's moving toward the east and the weaker one that's moving toward the west. So the next black and white image now shows this region with somewhat higher resolution. This picture was taken about 2 days later. This one, in fact, on the 21st of August. And now you can just barely see those two features that showed up so well in ultraviolet.
The pictures Voyager 2 sent back this morning were part of a sequence of photos shot 10 hours apart. Scientists were hoping they would show motion on the planet. Such motion would help them measure wind velocities and help them understand more about various weather conditions on Saturn. First, some photos of a region in the northern hemisphere which shows up as a great brown spot. Voyager 2 took photos of it Sunday night and again this morning. The two sets of photos showed a great deal of motion in the spot. They found that the spot is what is called an anticyclone, meaning a high-pressure region which moves in a clockwise direction. Imaging scientists Andy Ingersoll and Gary Hunt were, in their words, delighted with what they saw of the great brown spot, calling it their most important discovery of this morning.
Oh, very nice. And not only have you got the flow around it, there's also something occurring right at the very edge.
Yeah. This is an intriguing image, all this
and
ribbed.
Notice also that we've got one of the points, which is almost a characteristic of anything that has a large flow. The internal part is generally sort of symmetric in its flow, but you always get the barrier, the points being set up at the edge.
Yeah, you can just see, without even getting a time sequence, you can see these rotations this way.
More questions were raised about another phenomenon in the northern hemisphere region. This one, the ribbon-shaped configuration in the lower left-hand corner of this photo. Scientists are saying it is an eastward jet of wind blowing at about 300 miles an hour.
Now, there you are. There's a little spotty here, and there's the convection on the north side again. Yeah.
Ingersoll and Hunt had wanted to find out whether the ribbon was causing the great spot or affecting it in some other way, but this morning's series of photos didn't answer that question. Voyager scientists like Ingersoll and Hunt will spend the next several months poring over these pictures, mapping and measuring the surface of Saturn, becoming even more familiar with its various features. But right now, they are like excited campers getting their first glimpses of snapshots they took on their summer vacation. From the interactive room in Mission Control, Bill Griffith, NASA NewsNet.
In the press conference this morning, one unusual nude set of pictures was put out, that having to do with the small moon Hyperion. The pictures available so far show that this is indeed a very irregular object. That in itself is fairly significant. And the way it looked in the pictures we have so far, it didn't seem that they have its axis lined up right with its spin directions. But to talk about all of that and what this all may be and how it all may be disentangled, we hope, we have Joe Vaverka, a member of the imaging team. Joe, what about it? Is this an oddball object? First of all, it's awfully big to be so irregular. Isn't this a little unusual?
It certainly is an oddball object. I guess we don't know all the ways in which it's strange yet, but we're going to find out as we get a closer and closer look. I think it's true that the first views we got from Voyager 2 were rather surprising because, in fact, we were looking at the end which faces away from Saturn, and what we saw was a very rectangular cross-section, this is, I guess, the first picture we got. And the resolution here is something like 32 kilometers per line pair. And to the best of our estimates, the spin axis is in this direction.
Not lined up with the long axis.
And what we're probably looking at in this case is something that may have the shape of a chocolate bar. And you would normally expect that the long end of the chocolate bar would point at the planet, and that the flat end of it would lie in the orbital plane. This one came in at noon, yes, and...
There's some change of aspect between the two.
Yes, we're essentially going around towards the trailing side, and as I said, we're about maybe 40 degrees away from the anti-Saturn point.
One of the most interesting satellites of Saturn is Iapetus, the most distant large satellite from the planet. I'm here with Dave Morrison and Jeff Placia, who are Voyager imaging scientists. We're looking now at pictures of the dark and light sides of the satellite. And gentlemen, what do we know about why there is this dark side and the light side?
The light side is clearly water ice. We know that from ground-based observations. And we suspect that that is representative of the bulk composition of the whole object. But the simplest idea would then be that the dark material was somehow just a superficial thing laid down over the leading hemisphere, the hemisphere that faces forward as Iapetus goes around Saturn. But that's precisely what we're looking for. What can these pictures tell us about whether we have a superficial dark layer, or whether that's produced externally by stuff falling in, or whether it's somehow related to the activity itself. And particularly, we want to look at the individual craters and see how they relate to the light and dark.
The dark and light sides of Iapetus have nothing to do with the angle of light from the sun, but rather the intrinsic reflective surface of Iapetus. Morrison describes the difference in reflectivity of the dark and light areas as that of bright snow versus asphalt.
Leading theory to explain what happened on Iapetus is that the dark material came from elsewhere, namely from the outermost satellite of Saturn, Phoebe, and that it was chipped off of Phoebe in fine dust from impacts over billions of years, and this dust drifted inward, and Iapetus, on its leading side, as it went around the orbit, collected that dust. So it just painted the front of Iapetus dark, and the back stayed light.
Part of the light surface of Iapetus is splattered with craters. Part is quite smooth, as if an eruption of methane snow might have filled up the craters. The light side also has curious streaks that scientists had not seen before. Another new discovery in these pictures is a large crater with a dark floor, which may hold more clues to the ongoing geologic activity of Iapetus. The cameras of Voyager 2 have taken a series of photos of the satellite through different colored filters. These allow scientists to reconstruct a color picture of Iapetus and to get better information on the reflectivity of its surface. But still, they want to know more.
We are looking for a single explanation for almost everything, and that's because this is the first chance to look at it, and probably there is no single explanation, and there are different phenomena taking place. I'm focusing on what produces the dark stuff, and that may have nothing to do with what's producing some of the geological features that we're seeing.
Yeah, the thing we really need to constrain at are a lot of craters where we can see the floors if they're dark or if they're bright, and we just haven't been lucky enough to see it.
This is it. This is the highest resolution picture we're going to get of Iapetus in our lifetimes, probably.
Reporting from the interactive room at JPL, I'm Carol Ackright, NASA News Net.
And there's the outer edge of the A ring and the very narrow F ring that one can see very faintly.
One of its satellites apparently in the picture.
And Dione. Now, Dione is one of the satellites, icy satellites we visited very closely with Voyager 1, and actually we will not be looking at it as closely with Voyager 2. There are several, though, that we will be visiting more closely with Voyager 2, for instance, Enceladus and Tethys. Now, Iapetus also, we're seeing for the first time with resolution something on the order of 15 miles.
This is the one that has this curious marking. One side is many times brighter than the other. I heard that some material on the dark side is 10 times darker than that on the light side.
It's at roughly 10 to 1 brightness ratio. That's right. It's a remarkable object. This is Tethys. Tethys has a 500-mile-long canyon on it. We didn't image it very well on Voyager 1. With Voyager 2, we'll be able to resolve things as small as
now a little bit down at the bottom.
One can begin to see the canyon right at the edge of the image. That's right. And there is Hyperion.
That's what we're just beginning to see today and discover that it doesn't look right at all.
It just doesn't look right at all. That's right.
Of course, right now we're still approaching closest approach. After we go by, we'll then see Saturn in the South Pole.
Yes, we'll be looking at the dark side of the rings, the side that's unilluminated, and we'll be looking at the South Polar region of Saturn.
Going on to the satellites now, here is our 3 views of Hyperion. There have been all kinds of descriptions given for it, from a peanut to various other things. It is obviously very irregular. The scale is not the same in each of these images. It reflects the approach to Titan, this being taken at a distance of about 1.2 million, 0.7 million, and 0.5 million. So it's growing in size as the spacecraft gets closer. But the best description that I could give it right now is it sort of looks like a thick hamburger patty or whatever. And here you're looking into the edge of it. I wish I had a little model or something I could show you. But
one important science objective is the photopolarimeter observation of the occultation of a star by the rings. Light from the star, Delta Scorpii, is measured as it flashes through the rings in the shadow of Saturn. The 2¼ hour experiment provides information on the number of ringlets, their densities, and widths.
Now, that entire measurement lasts about 2½ hours. And I think we're just now seeing the beginning of the sequence, but they've obviously found the star. They're starting to make the measurement.
And they're getting in the data they expected.
It's a fantastic experiment when you think of the fact that the ring system, the distance from the inner edge to the outer edge of the ring system is tens of thousands of miles. It's comparable to the distance around the Earth. Yet we will measure detail there at the size of a city block.
And as you pointed out, we're already seeing thousands of rings, of small ring features. This map may show us a lot more even than thousands.
Yes.
The fact is, if the planetary program really has... I guess one way to look at today is the day of challenge, where we're going to be challenged by our new views of Saturn. I think it's fair to say that everything we're seeing today, basically everything we're seeing today, will be new.
I'd like to start off with the first slide, showing a filtered view, actually a mosaic of several images, just showing a filtered view of the very high latitudes on Saturn. There's a notch out the North Polar limb here, but one can see the enormous amount of structure that's up at the very, very high latitudes. Here we see some of these complex features, this brown spot that we've been looking at quite recently, now taking on morphology very similar to a spiral galaxy, and we're seeing material actually flowing out and forming rather curious patterns. Here is that high velocity jet, showing somewhat of a Rossby-like structure, Rossby wave-like structure, and associated with it are some cyclonic, that is the equivalent of low-pressure areas, in a system that's not altogether different from the Earth. This is the first view of Titan that we've released for the Voyager 2 encounter. It's not by any means our highest resolution image, and we'll perhaps release another at somewhat higher resolution. One can still see that it's a rather uninspiring orange ball, and but there is this north-south demarcation with a line which still is in there fairly close to the equator of Titan.
High-resolution photographs of the planet and satellites are assembled from mosaics of images covering separate areas of each target. From a distance of about 58,000 miles, Voyager 2's cameras compose a 4-image mosaic of Tethys.
Well, even though we're still, last night, 1 million kilometers away from Tethys, we did record a feature of rather curious appearance, a very, very large crater on one face of Tethys, a face that was not seen by Voyager 1. The crater is huge. In fact, it is the largest crater so far seen in the Saturnian system. It's about 400 kilometers, that is something in the order of 300 miles in diameter. We see a central peak. We see a ring of mountains that surround the impact feature. The central peak is caused by the rebound of material up from the center after the impact, and then as that central peak slumps back down, it pushes up the mountain chain that, or the mountain ridge that surrounds the impact crater of the planet. Well, there's an enormous amount of detail that's beginning to show up, and we expected this. This approach to Saturn with Voyager 2 giving us a good high-resolution view down on the illuminated ring system. Early in the approach by Voyager 1, we had estimated that there were hundreds of rings, and by the time we got through, that estimate grew up to perhaps something like 1,000.
And why don't we take a look at the zoom movie of Saturn?
I think it's a good way of seeing how dramatically the weather patterns have changed. You can see, particularly in the northern hemisphere, these bright cloud features bursting out. They're giant storm systems. Dark feature also are other clouds.
We can run it forwards and backwards.
If you stop it about there, Al, in fact, you can see that there are a large number of very bright patches in the region between about 20 and 40 degrees. And these
in the northern hemisphere.
In the northern hemisphere. And a large amount of detail is showing up there. And even if you look right towards the pole, you can start to see that the banding continues right the way up towards the pole. So there's a lot of detail and a lot of change in the basic meteorology of Saturn. We cannot see much in the southern hemisphere. The suggestion of spots is because we haven't got the optimum viewing. We'll see that better after encounter.
The data from the Voyager 2 Saturn encounter are still being analyzed by scientists. The rings were resolved into thousands of nearly concentric features, now thought to be shaped by the gravitational effects of the Saturn moons. Large bolts of lightning, as energetic as the total output of an Earth-based nuclear power plant, were detected in the Saturn B ring plane. Clouds in Saturn's atmosphere were clocked moving at speeds of 1,770 kilometers per hour. Saturn pictures were made by scanning instruments aboard Voyager. The pictures were converted to an electronic number code, and the numbers were transmitted to Earth via radio waves. Computers then used the numbers to reconstruct the images. During our next and final program in the series, we will look at what we know and what we expect to learn about the three outer planets, Uranus, Neptune, and Pluto. We will also talk briefly about comets, asteroids, and our hopes for the further exploration of space. Till next time, this is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.